Hey guys, Mr. Mark with a video over inverse trig functions and integration. So first thing is for this second formula for the second formula has tangent, let's slide in a 1 over a. I left that out in the notes. Also the same thing for secant, even though we will not use secant in this video in generally ever. All right, so the two formulas that we use primarily are sine inverse and tangent inverse. When we're integrating, the form for sine inverse has to be the square root of a perfect square minus a function that is also a perfect square. For inverse tangent, it is the sum of perfect squares on the bottom. Sometimes we will have to complete the square to get it into the proper form. We will do that in example 3. So if we start with example 1, the first thing that we have to identify is our a. A squared, is equal to 16. So a equals 4. U squared is equal to 9x squared. So u equals 3x. I can zoom in a bit. So if u is equal to 3x, we're back to a u substitution where du equals 3 dx and 1/3 du equals dx. So if we rewrite this integral, we have 1/3 times the integral of du over the square root of 4 squared minus u squared. And again, u was 3x, so if we square that, we do get 9x squared. So when we integrate this, it is in the form of the inverse sine function. So we will get 1/3 sine inverse of u divided by a. So u is 3x and a is 4. So we'll get 1/3 sine inverse of 3x divided by 4 plus c. So again, we identify a squared, identify u squared, and the way we get a and u is to take the square root of a squared and u squared. When we have the u, we take its derivative like we do with u substitution. So the derivative of u is du, the derivative of 3x is 3 dx. And then we do our replacement and we see that it matches its form, and so we integrate. For example 2, we have a definite integral, and it seems like this is in the form for inverse tangent. So our a squared is going to equal 25. So that means that a equals 5. Our u squared is going to equal 64 x squared. So our u is going to equal 8x. And so du equals 8 dx. And 1/8 du is going to equal dx. So a couple of things. Our limits for x are from negative 1/8 to positive 1/8. So x is negative 1/8 to positive 1/8. U is going to go from, if we substitute negative 1/8 into the u, that's going to be from negative 1 to 1/8 times 8 is positive 1. So the rewrite on our integral is 1/8, the integral from negative 1 to 1 of, let's see, du over 5 squared plus u squared, which according to our inverse tangent formula is 1 over a. So we have 1 over a, which is 1/5. We also have the 1/8 that we need to account for, and that's going to be tangent inverse of u over a. So tangent inverse, literally of, in this case, we can just do u over 5 because we don't have to go back to x because we have a definite integral. So we're just going to have u over a is actually equal to 5. And we'll evaluate that from -1 to 1. So this we can instead replace with -1 over 40. Not -1, I'm sorry. Why are we making negative? Just 1 over 40. So let's see. We can do, so it's tangent inverse of 1/5. So let's see. Tangent inverse of 1/5 minus tangent inverse of -1/5. And so it's that value, but then we multiply by 1 over 40, and we get 0.0099. We'll go with that. So this equals 0.0099. So for example 3, we have to complete the square, and that's just going to be a lead up to what we do for example 4. So in example 3, we have to complete the square. So remember, to complete the square, the term for the x squared needs to be 1. So that means if it wasn't 1, we divide everything in the expression by the coefficient on x squared. So since x squared is already 1, we don't have to do that. The next thing is you take half of b and you square that. So b is equal to -4. B over 2 squared is going to be, half of -4 is -2, and squared is going to be +4. So we add and subtract that to this expression. So we're going to have x squared minus 4x plus 4, but since we added 4 here, we also need to have +7 minus 4. So this equation really still is x squared minus 4x plus 7 because these two cancel out. So this always factors to be x plus b over 2 squared. So half of b is -2, so we're gonna have x minus 2 squared is how this factors, and then that's gonna be +3. So we've completed the square, and that's gonna be necessary to complete some of these inverse trig functions. For example 4, we have to integrate this. Now, our first thought is if we see a rational function, we should try U substitution because maybe it turns into like a natural logarithm. And later when we do partial fractions, there's another way to do this. But partial fractions won't work, and neither does regular U substitution. So we want to complete the square on this. Now, fortunately, we already did this in example 3. So we know that this is equivalent to having dx over x minus 2 squared plus, so let's see, we'll say a squared equals 3, that means a equals the square root of 3. So we're gonna have this as the square root of 3 squared. And again, that's based on what we did right here. We already completed the square so that we got this. So that's what we're using for example 4. So again, we have a rational function, no square root. So this is a good indicator that we're gonna have inverse tangent. So a squared is equal to 3, a is square root 3. U squared is equal to x minus 2 squared. And so u is x minus 2, and du equals dx. So as a final answer, we can rewrite this to be du over u squared plus square root 3 squared, which equals, again, 1 over a times tangent inverse of u, which is x minus 2, over a, which is the square root of 3, plus c. So we went back to x's because we did not have a definite integral. For example 5, we have a square root on the bottom. So we have, this is probably going to be inverse sine. We also have a negative x squared plus 6x. So let's first complete the square with this. We have negative x squared plus 6x. So we're going to factor out a negative. So we have a negative times x squared minus 6x. Now, if we're going to complete the square, half of negative 6 is negative 3. When we square that, that's going to be 9. So we're going to have negative x squared minus 6x. And then, again, half of negative 6 is negative 3. Squared is plus 9. And so we need to also cancel out this 9. But remember, we have to take the 9 out of the parentheses. So it's going to be a negative 9. So here we actually want to do a plus 9. So this is going to turn it, so like, let's finish this out. So we get negative x minus 3 squared plus 9. So the rewrite for this integral is going to be the integral of du over the square root of 9 minus x minus 3 squared. And so this is in the form of an inverse sine integral. So we'll write in a different color. Let's go with this blue. So a squared is equal to 9. And so a equals 3. U squared is equal to x minus 3 squared. So u equals x minus 3, and du is equal to dx. So the rewrite on this integral is, this should be a dx, by the way. I don't know why I put du. So we get the antiderivative of du over the square root of 3 squared minus u squared, which is, we'll write it down here, sine inverse of u, which is x minus 3 over a plus c. For the next example, so sometimes it's going to appear that we can do an inverse trig function with the integral as we currently have it, but we're going to separate this into two different integrals. Excuse me. So if we didn't have the 2 in the problem, let me see. If we didn't have the 2, I'm still covering this up, all right? So here we go. If we didn't have the 2, then we could do this integral by u substitution. We could let u be 4 minus x squared, and the derivative is negative 2x. And so that allows us to get rid of the x. So if we can split this into 2 separate integrals, we can work on one using u substitution, the other using an inverse trig function. So our rewrite is, this is going to equal the integral of, anytime you have a single term in the denominator, we can make this x over the square root of 4 minus x squared dx plus another integral where we have 2 over the square root of 4 minus x squared. We'll put another dx. So this one uses u substitution. This one is an inverse trig integral because it's a squared minus u squared. This one is, so we'll work both. For this first integral, for integral 1, we have u equals 4 minus x squared. So du is equal to negative 2x dx. And so negative 1/2 du equals x dx. So the rewrite for the first integral is negative, oh, you can't see. So the rewrite is negative 1/2 times the integral of du, so this is 4 minus x squared to the negative 1/2. So we're going to have u to the negative 1/2 du. And if we integrate this, we're going to get negative 1/2 times u to the 1/2. And so we divide by 1/2, which means we need to multiply by 2. And so that would equal negative u to the positive 1/2 plus c. So for this first integral, if we write that back in terms of x, we would have negative 4 minus x squared to the positive 1/2 plus c. So that's from the first integral. From the second integral, since it's some number over a squared minus u squared under square root, we know a squared equals 4, a equals 2, u squared equals x squared, and so u equals x, and du equals dx. So in order to just save time here, since all of this is just switching variables around, this integral, we'll put 2 here, this integral is equal to sine inverse of u over a, so x over 2 plus c. But don't forget we had the 2 in the top, so we're going to multiply by 2. So the answer to the sum of these two integrals is this result plus this result. So the final answer, which we'll write in, we'll say brown, is negative 4 minus x squared to the 1/2 plus 2 sine inverse of x over 2 plus c. So again, the trick that we did was we split this integral into 2 separate integrals that we could evaluate. In doing so, the first one gave us an integral that could be solved using u substitution. The second gave us an integral that could be used solving an inverse trig function. And we won't do example 8. We'll just take that out. The last one is example 7. So example 7 is very similar to example 6, except we're going to do a pretty clever trick. Like, imagine we had a u substitution where u equaled x squared plus 8x plus 25. Then its derivative would be 2x plus 8. So the problem is on the top, we have 2x plus 5. Now, the good thing about math is as long as we add the same thing to an equation, an expression, we can keep it balanced. So imagine we rewrite this to be 2x plus 8. And then to make this, to still have a 5 in the numerator, we would need to include a minus 3. And we can do that over x squared plus 8x plus 25 dx. So just like we did on example 6, we can then split this integral to be the integral of 2x plus 8 over x squared plus 8x plus 25. That's one integral. We need to include the dx. And then we're going to have this other integral, which is minus the integral. And the minus is because of this negative. So minus 3 over x squared plus 8x plus 25 dx. So this one's going to work by using u substitution. This one, we're going to do completing the square to get an inverse trig function. I mean, to get it in the form for inverse tangent. So, all right. So we already know that this is in the form of du over u. So this first integral is going to be the integral of du over u. And again, that's because u is x squared plus 8x plus 25, and du is 2x plus 8. So this is du over u. So immediately, we know that that's the ln of the absolute value of u. Now this other integral here, if we complete the square with x squared plus 8x plus 25, half of 8 is 4, and then 4 squared is 16. So we're gonna have plus 16, but then we need to do plus 25 minus 16. This is a net value of 9. So this factors to be x plus 4 squared plus 9. So the rewrite on this integral is minus the integral of 3 over x plus 4 squared plus 3 squared. So a squared equals 9, a equals 3, u squared equals x plus 4 squared, u equals x plus 4, and du equals dx. So the same, we don't actually need to do a replacement because du is exactly equal to dx. So when we rewrite this, we're gonna have minus 3 times 1 over a, so 1/3 tangent inverse of u, which is x plus 4, divided by a, which is 3. So the 3 and the negative 3 cancel out. So this entire integral is the ln of x squared plus 8x plus 25 minus tangent inverse of x plus 4 over 3 plus c. So that concludes this pretty lengthy video over the integrals of inverse trig functions. The two that we covered are inverse sine and inverse tangent. So for inverse tangent, you will have a rational expression where we have a squared plus u squared. And we identify all of the information here and put it into an integral that can be solved. For inverse sine, we have the square root of a perfect square minus another perfect square, and we still identify all of our information. If we have a meaningful u substitution, we actually do that replacement and we integrate. I would recommend doing these problems for practice. Thanks.